So next time we'll talk about winds and weather on other planets, including Jupiter and Saturn. But for the rest of today, we'll talk about the atmospheres of Earth, Mars, and Saturn's moon Titan. So what makes the atmospheres of Earth, Mars, and Titan different to each other? Well, it depends partly on how much heat they receive and what they do with it. We can ask what controls the temperature of solar system bodies, and this picture sort of gives it away. The sun is the main source of heat for Earth and for many other bodies in our solar system, including Venus, Mars, and Titan. The heat travels to each planetary body through space in the form of radiation. And this radiation is absorbed by atmospheric gases, clouds, hazes, dust, and also the surface of the planet. Some planets and moons do have internal heat sources too, and this internal heat can come from a range of different things. In general, the more mass of the planet, the more internal heating it can generate. And the gas giants Jupiter and Saturn both generate slightly more heat internally than they receive from the sun. So internal heating is also responsible for driving the wind and weather in their atmospheres. Just as an aside, why are they called gas giants? Well, first of all, they're giants. They have radii about 10 times the Earth's, as you can see from this picture that is to scale. The Earth barely fits into the great red spot there on Jupiter. But despite their size, they're mostly made up of hydrogen, and they probably only have a tiny ice rock core. We can't know for sure just yet. And then near the top of their atmospheres, they're mostly hydrogen gas. But deeper down, we think the pressure becomes so large and temperatures become so high that the hydrogen starts to behave like a liquid metal. And again, we'll talk more about these planets next time. But back to bodies for which the sun is the main heat source. What is it that decides a planet or a moon's temperature? So I've put 3 equally sized planets at different distances from the sun. And you can immediately see that there are more rays of energy going through the closest planet than the next one out, and more through the middle one than through the one that's furthest away. So basically, the further a body is from the sun, the less heating it receives per unit surface area. Heating per unit surface area actually goes down as 1 over the distance to the sun squared. And that means that Venus, which is closer to the sun than the Earth, receives about twice as much heat as Earth per unit surface area. And Mars, which is further away than Earth, receives about half as much heat as Earth per unit surface area. And Titan, which is all the way out in orbit around Saturn, only receives about 1% as much heat as Earth per unit surface area. Now, if a planetary body has no atmosphere, it's fairly easy to work out, or at least, estimate what its average surface temperature would be. We have to consider the incoming solar radiation, which, as we just said, depends on the distance to the sun. And then we have to realize that some fraction of that is going to be reflected. Now, the amount that's reflected will depend on the planet's brightness or its albedo. A high albedo means that lots of solar radiation is reflected. The body absorbs the rest of the radiation, which goes into warming it up. However, any warm body also emits thermal radiation, and that's true of you and me as well. The amount emitted depends on the surface temperature. So if we put this all together, the incoming solar radiation must equal the outgoing radiation, which is given by the reflected solar radiation and the emitted thermal radiation. Otherwise, the body would warm up or cool down over time because there would be an imbalance. And that means that the surface temperature of a body with no atmosphere is given by whatever temperature makes the incoming and outgoing radiation equal. So we can work out what the surface temperatures of Earth, Mars, and Titan would be if they had no atmospheres, and if each had a surface albedo of 0.25, meaning that a quarter of the solar radiation that comes towards the planet gets reflected back again. So for Earth, the estimate is 258 Kelvin. And here K stands for Kelvin, which is a type of temperature scale in which 0 is the lowest possible temperature at which all molecules stop moving. And we use Kelvin a lot in planetary science, and it works out to about 5 degrees Fahrenheit. So this is well below freezing, so that probably doesn't sound quite right for the Earth. On Mars, the estimated temperature would be 210 Kelvin, so considerably colder, minus 82 degrees Fahrenheit. And on Titan, it's hugely cold, only 82 Kelvin, which is a whopping minus 312 degrees Fahrenheit. So how do these estimates compare to the actual surface temperatures? Well, for Earth, the actual temperature is 288 Kelvin. And so the effect of the atmosphere is a 30 Kelvin warming. For Mars, we get 215 Kelvin, so there's a relatively small 5 Kelvin warming due to the atmosphere. And for Titan, we get 93 Kelvin, which gives us an 11 Kelvin warming. So why does its atmosphere change the surface temperature of a planet or moon? What's going on? Well, atmospheres contain gases, clouds, and other things that absorb and or scatter the radiation that passes through them. So the surface temperature of the surface and of the atmosphere depends on what gases the atmosphere is made up of, how much atmosphere there is, and what clouds, hazes, and dust particles are in the atmosphere too.